and welcome. I'm Uğur Demirkol, and in this video I'm going to talk about the magnetic force experiment. The purpose of the experiment is investigating the magnetic force on a current carrying wire in a magnetic field depending on current, magnetic field, and length of the wire. We will use a scale, 6 U-shaped magnets, a magnet holder, 6 current circuits, main unit that attaches to the current circuits, a DC power supply, an emitter, and few connection cables. Let's discuss some theory behind the magnetic force. Electromagnetic force, which is applied onto a moving charged particle, is described with Lorentz law. Which is force equals charge of the particle multiplied with electric field and plus the vector cross product of the velocity of the particle and the magnetic field applied. We are not going to use an electric field in our experiments, so we can summarize this equation like this. We have a vector cross product here, so let's draw a Cartesian coordinate system here. We have x-axis, y-axis, and z-axis. Also, let's draw a wire along with z-axis, and we have some charged particle with velocity of v here, and also we have magnetic field along y-axis as well. And let's find the force, the direction of the force which is applied to this charged particle. Well, when we are doing vector cross product, we calculate this as this. Let's call the axis as I, J, and K. When we calculate the quantity, vectoral quantity in I plane, in I axis, with J, with some quantity in J axis, I mean it is when it is like this. We take the positive sign to, we would have a positive sign, a new quantity along with k-axis, and when we calculate these from I to J, J to K, K to I, we will all have positive signs. But when we go in backwards, like I to K, we will have a negative sign, vector product, along with J-axis. So when we go backwards from this, we would have minus signs. So we have an x-axis here, we have velocity on z-axis, and magnetic field on positive y-axis. So as you can see, you can call them x, y, z as well. We will go from z to y, so it will get a negative sign. So the force applied will be through this screen. Let's show the force here. Okay. Well, when a current passes through a wire, it would have a lots of charge carrying particles like electrons. It won't be one electron. There will be maybe millions or billions of electrons or charged particles. So we can expand this equation like this. The net force is equals to number of charged particles and the charge value of them and the drift velocity, average drift velocity of charged particles and the magnetic field and the vector product. So but let's discuss the total number of charged particles in the wire. We can expand this like like this. The volumetric density of charge carrying particles times the cross section of the wire and the length of the wire. If we consider the wire something like this will be the cross section and this will be the length. So our equation becomes like this. Also we have a useful tool to further fit our equations into our experiments. Let's talk about the magnitude of the current density, which is given by J, which is equals the number of the charge carriers per volume times the charge and their drift velocity. We also know that a current can also be described with the magnitude of the current density times the cross section. If we do some calculations, the current will be equal to this. So we have these quantities on our Lorentz law equation, which we derived earlier. So let's put them in there. this is Q. And it comes like this. The magnetic force can also be described in terms of currents and a displacement vector L, which can be this. And we can replace the displacement vector with drift velocity vector, since the charged particles uh, moves along with the wire. So it becomes something like this, which was the magnitude of the current density. So our equation finally becomes in terms of the current times the product of vector product cross product of displacement vector and magnetic field. So if you do the vector multiplication for its final magnitude, we would have currents and the magnitudes of the vectoral quantities and the angle and the sine function of the angle between them, let's say theta. In our experiments, the displacement vector of the wire and the magnetic field will be perpendicular. So since theta will be equal to 1. So we can simplify this equation into current, length of the wire, and the magnetic field, since this would be the 1. We have an experimental setup like this. We have a DC power supply on the right side. We have a scale. We have magnets, which is we have 6 magnets which are in the magnet holder, and we have a current circuits carrying apparatus here and some connection cables. Also, let's talk about the procedure of the experiment. We will be conducting this experiment within 2 parts. At the first part, we will change the current values by 0.5 amperes at each step. Firstly, we should measure the mass of the magnets without opening the power supply, and we should recall this value as well. Then we are going to open the power supply and adjust to 0.5 amperes current value. Then we increase to 1 ampere. We will be doing this by 0.5 ampere steps. After that, we will have this data. Firstly, we should have picked a current circuit, and we should record the length of the wire, which is 2.2 centimeters, and we have current values here, and the mass of the mass value that we read on the scale will be recorded in here. As you can see, when we increase the current values, the mass is also getting increased due to magnetic force. Also, we should differentiate this value, the mass value, when we measured when there is no current on the circuit, from the other values, and record them on these. And then we will calculate the force by multiplying with the gravitational acceleration value, which is 9.81 meters per second square. And we plug the force to current. We will have a graph like this. Then we fit into a linear function, and we will have this line here. So the slope of this line will be equal to difference in force over difference in current. We have a derived equation here. So our slope will be equals to length of the wire times the magnetic field. So the calculated slope here is 3.96 times 10 over minus 4 Newton over ampere. So we have the length of the wire, which was 2.2 centimeters, and then when we calculate this, we will have 0.018 Tesla magnetic field, which is equals to 18 milliteslas. Tesla is the unit of the magnetic field in the SI unit system. Then we can discuss the procedure of this experiment, the second part of this experiment. In this part, we will change the length of the wire by changing the current circuits. Firstly, we remove the magnet from the scale. Then we remove the current circuit from the apparatus. This should be done when the power supply is shut down. And we replace with another current circuit. Then place the magnets. We will be conducting this experiment at 5 ampere current. Then open the power supply. After closing the power supply, we can change the other to other current circuit. In all these experiments, we should never uh, interfere with the scale. We should never touch it. We should never shake it to measure correct mass values. And we will repeat this for 6 different current circuits. Here's our data from this part. We have current of 5 amperes. For when there is no current passing through the wire, the measured value of the mass of the magnet is here. We have the code names for current circuits, which are written on the current circuits, and the corresponding lengths for these current circuits, the measured value of mass from the scale, and the difference between this value from these values, and also same calculated force values, which are difference between mass values times the gravitational acceleration. So if we plot this force to length, we will have a graph like this, and if we fit to a linear function, we will have a line like this. But our slope is different from the first part. Our slope in this graph is the difference in force over difference in length of the wires, which is equals to current times the magnetic field. So our slope is 9.04 times 10 over minus 2 Newton over meters, where our current is 5 amperes. So when we calculate the magnetic field, we will also achieve 18 milliteslas as well. Let's discuss some results. By the way, I would like to hear your comments on this experiment as well. My thoughts on this experiment is like this. A current carrying wire under a magnetic field creates magnetic force. Magnetic force depends on the current intensity, the wire length passing through the magnetic field, and the magnetic field intensity. When the direction of the current and the magnetic field is perpendicular to each other, the magnitude of the magnetic force takes the maximum value. As required by Newton's third law of motion, the magnetic force was created in the wire was applied to magnets equally in the opposite direction. So this enabled us for measuring the magnetic force with a scale. Thanks for listening, and I hope you the best.